Okay. So I actually changed my mind about when the midterm would be posted. I will post the midterm this afternoon. And I will leave it posted all weekend. So it is due before Monday. Our class starts at 10 a.m., so we'll make it 10 a.m. Hopefully, and correct me if I'm wrong for anybody, hopefully no matter how hectic your schedule is, yes, Jalen?
Oh, keep going.
Hopefully no matter how hectic your schedule is, that should fit in somewhere. There will still be a time limit. Let's say 1.5 hours, and that includes the time to upload. So once you take a look at it, then you have 1.5 hours to finish it. It is closed book and closed notes once you start. And do it by yourself. But I'm happy to answer any questions that you have. You're welcome to work together before you start. So anytime this weekend, up until 10 a.m. Monday morning, feel free to do that, to do the test. Now, yes, but Jalen, you had a question.
So is it going to be like in the same format as you do the homeworks, or
No.
we have to like print it out?
It'll be, you don't have to print it out. You can write it on a piece of paper, but so let me talk about that now. So do on paper. You can, if you have a printer at home and you want to print it out, that's great. I will leave space for you to do it that way. But if you don't have a printer, not everybody has printer or ink or whatever. So you just do it on a piece of paper, take a picture with your phone and upload it to, I will share a Google Drive with you today. So do on paper and I'll share a Google Drive.
Will the test be in the Google Drive?
Nope, test will be on our webpage.
Okay.
These are all good questions.
And I know Moodle does timing tests, but is yours just like honor code?
It's just honor code, yeah.
Okay, got you.
I'm going to do my best to make this not a race against the clock. I put the time limit on it, not so much because I want you to rush, but because when I don't put a time limit on it, I tend to write exams that are too long and too difficult. And I really don't want to do that. What I want to make sure is that you have the basic skills, and the way to keep myself in check is to put a time limit on it.
Fair enough.
Okay, so let's see. As far as the logistics of the test go, did I miss anything?
On the syllabus, it says it covers 3.1 and 3.2.
I'll tell you exactly what it covers. I'm gonna go over exactly what this covers. Yeah, we haven't done 3.1, 3.2 yet. I will tell you exactly what this covers. So in fact, I can start right now. This will cover chapters 1 and 2. Only the sections we talked about. In fact, I'm going to tell you exactly what's on it. This semester, especially because of our unusual situation, I want to make sure that I can give you all the support and make sure that you just come out with the skills that you need to have from this course. That's my ultimate goal. So let's see what's on the test. Well, before I get to that, is there anything else about logistics that I haven't said yet? Okay, so seem to be good. So what do you need to be able to do? You need to be able to solve a system of linear equations or a vector equation or a matrix equation or an augmented matrix. These are just four ways of writing exactly the same thing. Be able to go back and forth between all these things. And you should be able to write your solution in parametric form. To be able to solve and write your solution in parametric form. You should be able to row reduce. To be able to put a matrix into reduced echelon form. Tell me where the pivot positions are. You should be able to tell me whether a matrix is invertible, and if it is, find the inverse. You should be able to tell me whether a set of vectors is linearly independent. You should be able to say whether a set of vectors spans. you should be able to describe linear function or transformation geometrically. This one is a reflection over the horizontal axis. This one is a rotation of 90 degrees. This one is a stretch, vertically. This one's a stretch horizontally, and so on. I think that's it. I think that's all. And I'm going to spend the rest of today's class practicing with you, so that when you get to this, you feel perfectly confident. So solve this and write your solution in parametric form. I highly recommend working as an augmented matrix. It's the easiest way, least writing. Before you start anything, write that system of equations as an augmented matrix. Let me just make sure I didn't make the computations awful. Yeah, I think we're good. So don't wait for me. So hopefully you convert it to an augmented matrix like that. How's it going? So we're going to row reduce. Remember your plan as you row reduce. Start by making sure there is a 1 in your first pivot position, assuming there's any way of doing that, assuming there's a pivot position in the first column, but there's some non-zero stuff in this first column, so there is. We already have a 1 there. Get zeros below it. Then make sure there's a 1 in your next pivot column. And sort of move down into the right. And then clear the stuff up into the, sorry, and then clear the stuff at the top right. So I'm going to take row 2 and subtract off 2 times row 1 to get a 0 there. And I think at the same time, I'm going to take row number 3 and subtract off 4 times row 1. So 0, minus 1, minus 3, minus 11. Now I want to get a 1 here. So negative 1 times row 2. I'll leave row 3 alone for a moment. If you're going in a slightly different order than I did, I'm not going to make a big deal about that. As long as all your row operations are correct and we end up in the same place. Okay, so I want to get rid of the stuff below that leading 1, so I'm going to add row 2 to row 3. Not do anything to row 2, but in row 3 I'm going to add row 2. So that's 0, 0, 0,
Isn't it supposed to be a negative 1 in row 2?
Where?
On your top right, you have a negative 1 in the second row.
Here?
Yes. And then in the left.
So are you saying going from here to here?
Oh, okay. I see what you did. Never
Yeah, I
mind.
just multiplied the whole row by negative 1. I just wanted to put a 1 in the pivot position. So I already had a 1 in this pivot position. I wanted to make sure there was a 1 in this pivot position. And I had a negative 1 in there before, as you observed. You might have just done things in a slightly different order than I did. You might have cleared out row 3 before you change that to a 1, and that's fine. So now we have a 1 here, a 1 here. I want to make sure that I get a 0 above all the leading entries. So there's a pivot position here, there's a pivot position here. I want to make sure that I get a 0 above all the pivot positions. So I want to make sure that that's 0 now. So I will take row 1 and subtract off row 2. And I get 1, 0, -2, vertical bar, and what's -5. I will take 0, 1, 3, 11, 0, 0, 0, 0. And I am in reduced echelon form. All my leading entries are 1. They're the only non-zero things in their whole column. All my rows of 0 are at the bottom. Now I can go ahead and write my answer. This first row says that x1 minus 2x3 equals -5. And my second row says that x2 plus 3x3 equals 11. And x3 is 0. Sorry, x3 is 3. Now I want to write this in parametric form. So I'm going to write x1 equals minus 2x3 minus 5, subtracting them, plus 2x3 minus 5, adding 2x3 to both sides. And x2 equals, actually, let me do it instead of, let me do this in a different order. Let me put the letter in first. I'll use S. So x3 will be S. So x1 minus 2s equals -5. x2 plus 3s will be 11. And x3 is just S. I use a letter for every one of my free variables. That's an S, not a 5. Let me continue that over here. So I have x1 equals 2s minus 5. x2 equals minus 3s plus 11. And x3 equals S. And I guess I could go ahead and write this in vector form if I wanted. x1, x2, x3 equals 2s minus 5 minus 3s plus 11 s. In other words, x1, well, let me just rewrite this. In other words, 2s minus 3s s plus 5 minus 5 rather 11 0, and I get back the s out of this. 2 minus 3 5, sorry, 1. That looks like a 5 to me. Yes. plus minus 5, 11, 0. So these are all basically the same answer written parametrically. And then again, this is an S. But here it's clear what my solution actually is. You can see it's a straight line through this point parallel to this vector. Straight line through that point parallel to this vector. It's a straight line because I have one free variable. If I had two free variables, it would be a plane. If I had three free variables, it would be something we don't really have a name for, hyperplane, if you like. Did anybody have trouble with the row reduction?
A little bit.
So which part?
So I understand like the trying to get like the part that's on the left, but like past the vertical line, that's where I don't get how you got those.
You mean these numbers over here?
Yeah.
Oh, so when you do a row operation, you don't stop at the vertical line. You do everything that you do over here, you also do on the right-hand side. So for instance, when we started with this, and we took row 2 minus 2 times row 1. So it's 2 minus 2 times 1 is 0. 1 minus 2 times 1 is -1. -1 minus 2 times 1 is -3. And 1 minus 2 times 6 is -11.
Okay.
So the vertical bar doesn't insulate anything. You just keep going.
Okay. I'll make a note of that. Thank you.
Sure. Are there any other questions about the row reduction? I mean, the row reduction is sort of our bread and butter. So I want to make sure that everybody's really comfortable with it. Is that okay? Okay, great. Yeah, so practice, there's a bunch of row reduction problems you can do in the book. Just practice. So remember that when you're getting down to reduced echelon form, you want every leading entry in each row, assuming there is one, there's no leading entry here, but assuming there is one, you want it to be a 1. You want that 1 to be the only thing that's not 0 in its column, and you want all the 0 rows to be at the bottom, and you want the leading ones to go down to the right. So when you're looking at this, you see right away, there's no leading entry over here. This is definitely a free variable. X3 is a free variable. X1 and X2 are not free variables. How about this? One of you better say something. If you start working on this, no, just say something. Look back at the question you just finished.
They're the same.
It's the same question. This is the same question. What about this problem?
Same thing.
It's the same question. Has the same answer. It's exactly the same question. What about this? Not the same question. But you don't have to start from scratch again. Give me one solution to this without breaking a sweat.
Oh, x1, x2, and x3 are 0.
If x1, x2, and x3 are 0, of course the left's going to be the right. The trivial solution, the all zeros, is always going to be a solution to a homogeneous equation where the right side is 0. Is that the only solution?
No, because there's going to be a free variable.
There's a free variable. So if you take a look at your answer from the first one, we had s times a vector plus another vector. If you have the, if you do the, all I did is change the right side to zeros. You're just going to have, so what was the vector that went right after the s? 2 minus 3. If you take a look at your solution for the first one, 2 minus 3. What goes in the third entry?
1.
1. If you go to the homogeneous solution, you're going to end up with exactly this. You're going to do exactly the same thing, except you're not going to have plus anything. It's just goes through the 0 vector. So it's the, you don't have to start all over again. This is basically the same question, only the homogeneous version. And so you don't have, before we had plus and then some other vector with a -5 and 11 and a 0 in it, I think. But this time you just don't have that. What about this? Are the vectors 1, 2, 4, 1, 1, 3, 1, -1, 1, linearly independent? You've already done the work. You shouldn't have to start again.
No.
No. Why not?
Because we can have other solutions other than the.
Because there are others. There's a, when you row reduce this matrix, there's a free variable. There's going to be a column without a leading entry. So we had a free variable. So when we row reduce, um, 1, 2, 4, 1, 1, 3, 1, -1, 1. We had no leading entry in that third column. There's a free variable, which means, as you said, there are other solutions to this equation, not linearly independent. Do the vectors. One, 2, 4, 1, 1, 3, 1, -1, 1. Span R3. I see, Jalen, I see you shaking your head back and forth. No, you're right. How do you know?
Because you said it only goes up to one one, right? Because it's linear. It's not like a plane or beyond that.
Oh, okay. So not quite. You're confusing the solution to this matrix equals 0. So, but you're on the right track. You're on the right track. So these three. So if you write this as a matrix, 1, 2, 4, 1, 1, 3, and in other words, the matrix we've been writing the whole time, 1, -1, 1, and you row reduce. In order for this to be linearly independent, you'd have to have a pivot position in every single what? In other words, for them to be linearly independent, you have to have a pivot position in every single what?
Column.
In every single, hang on, let me just think about that for a second. Linearly independent. You have to have a pivot position in every single column, right? In order for them to span, you have to have a pivot position in every single what?
Column.
No,
Oh,
linear. So for them to be linearly independent, pivot position. I asked two separate questions there. Pivot
Okay.
position. In every single column. For them to span, you need a pivot position in every single what?
Row.
Row. Either way, we saw there's a pivot position here. We saw this pivot position here. There's no pivot position in the third column or the third row. Once you have three vectors in R3, if they don't span, they're not linearly independent. And if they're not linearly independent, they don't span because it's a square matrix. Do these two vectors span R4? They're both vectors in R4. Do they span R4? You shouldn't have to do any computation for this.
No.
No. Yeah, no. There's no way two vectors can span all of R4. At least how many vectors do you need to span all of R4?
4 vector.
Four, right, at least four. And you can see that these two vectors can't span R4 because if you wrote them as, I mean, you don't have to do this, but 1, 3, 5, 7, and then 1, -1, 1, -1. If you wrote them as a matrix like that, the columns of a matrix, we know they only span if you have a pivot position in every row. There are 4 rows. What's the most number of pivot positions that matrix could possibly have?
2.
2, right. So there's no way to have 4 pivot positions. There's no way to have a pivot position in every row. You can't have more pivot positions than you have columns. So right away, you can see that these two vectors, you can never have 2 vectors that span R4. 2 is smaller than 4. Are these 2 vectors linearly independent? With 2 vectors, it's easy to figure it out. You don't have to do any computation. Are those 2 vectors linearly independent?
Yes.
Yes. So again, with 3 or more vectors, it's harder, but with 2 vectors, it's easy. How can you see right away that these 2 vectors are linearly independent? They're not what?
That's like multiples of each other.
Yeah, they're not multiples of each other. They're not parallel. 1, 3, 5, 7 is not parallel to 1, -1, 1, -1. They're not multiples of each other. Are the vectors 1, 2, 3, 5, 7, -1 linearly independent?
No.
Excellent. Why not?
Like what you said last time, they're not multiples of each other.
No. So with 2 vectors, it's easy to see whether they're linearly independent or not. The only way they can be linearly dependent is if one's a multiple of the other. With 3 or more, it's hard to see whether they're linearly independent or not. But it's still easy to answer this question. Are these 3 vectors linearly independent? Again, you do not need to do any computation to answer this question. All you have to do is count. So your
There's
answer,
not going to be a pivot position in every column.
yeah, there can't be a pivot position in every column. You can't have these vectors are in R2. They each have 2 entries. What's the maximum number of vectors in R2 that could be linearly independent?
2.
2, and I have 3. So the answer is no, too many vectors, but Kayla, you explained exactly why. If I write them as the columns of the matrix, there's no way to have a pivot position in every column. There's no way. If I asked you whether those vectors span R2, now you have to do a little bit of work. Now you have to make sure that there's a pivot position in every row. It turns out there is. But at least that question isn't completely obvious. Completely obvious. At least that question requires a little bit of computation. So say V1, V2, V3, V4, and V5 are vectors in R11. Do V1, V2, V3, V4, and V5 span R11?
No,
No. How do you know that?
there's not enough.
There are not enough of them, right? If I wrote them as the columns of a of a matrix, I would have this matrix with 11 rows and 5 columns. There's no way to have a pivot position in every row. I can there's no the maximum number of pivot positions I can have is 5. If I asked you whether those vectors are linearly independent, did I give you enough information to answer that question? Yeah, there's no way you can know based on what I told you so far, right? Those vectors could be linearly independent or not. I can't tell based on the given information. All I said is there are 5 vectors in R11. So say V1 and V2, V3, V4, and V5 are vectors in R3. Are V1, V2, V3, V4, and V5 linearly independent?
No, you can't have pivot position in every column.
Yeah, I have too many vectors there. The most number of vectors that could be linearly independent in R3 is 3. I have 5. That's too many. And as you said, there's no way to have a pivot position in every single column if I wrote these as the columns of a matrix. If I asked you whether these 5 vectors span all of R3, did I give you enough information?
No, we would have to.
Yeah, I mean, maybe they span all of R3, but they don't have to. Maybe V2, maybe all these vectors are parallel, or maybe they all lie in the same plane. Geometrically speaking, what does that matrix do? You can see what it does to a specific vector, x1, x2. If we multiply that, we have x1, we have 2x2. So it makes the second coordinate twice as big. Geometrically speaking, how would you describe that?
A stretch.
Yeah, it's a stretch, exactly. It's a stretch in the x2 direction. So how do you feel about what we talked about today? Is this making sense?
I feel a lot more confident than I did last night. So
Good.
Yeah, it was very helpful.
Okay. I think you guys already know this stuff. It's just sometimes hard to know what it is you know and what you don't know.
exactly.
Well, again, if you have any questions, I will be available to answer them. Just send me email and I will do my best. If you need to talk to me, we'll set up a mutual time. But you'll have all weekend. And if you get it in by Monday morning, I'm totally happy. Let me know what else I can do.
I appreciate you extending the time as well.
You know, I was just thinking about it, and there's really no point in me trying to restrict it to one afternoon. That doesn't help anybody. And I can see that a lot of you have, jobs that you have to coordinate with, and I'm just not going to, there's no point. So if hopefully by Monday morning suits everybody's schedule at some point. If I'm wrong, then just let me know, and I'll, in advance. Don't wait till Monday morning to tell me, and I'll do whatever I can. But really, my main goal is to make sure you finish this course with the skills you'll need to take into your upcoming courses. Are we good?
Yeah.
Okay. I will see you all on Monday, unless you have some questions before then.
See you in a couple minutes.
See you in a couple minutes, right?
Thank you.
My pleasure.